So we're going to talk about, probably I think the way that this should be taught, obviously that's why I'm teaching it, but we're going to look at arithmetic sequences and geometric sequences. And last lesson we looked at arithmetic sequences, and that was where we had a common difference between our terms. So when we added a value, what was the value called in the equation? Which letter represents the value we add each time? D, which is our common difference. So if we wanted to determine the sum of all previous terms in an arithmetic sequence, we would use this formula. And all this is doing is taking the average between our first term and our second term as far as I'm concerned, which we can do with these styles of, because it's a linear equation, we're essentially picking 2 points and going with that. But all you need to know is that this is the formula given on our formula sheet, so this is one where I'll be encouraging us to use it. What is actually going on? So if I looked at a sequence on the board, someone give me an arithmetic sequence. Give me a first term, Max. 10. Give me a second term, George.
8 million.
8, good term. Next term?
6.
Okay, etc., etc. If I wanted to know S5, I could shove it into that equation, but it's important that I understand what that means. And what that essentially means is 10 plus 8 plus 6 plus 4 plus 2, which we would see as 30. And we can prove those equations work. 10 plus 2 is what? 12. N is 5. 12 times 5 divided by 2. Cool? So as long as we understand what's going on, we know what these values mean in our equation. What's T1? First term. Tn changes depending on what term we're being asked for, but it's the last term in the sequence. And n is simply the number of terms in the sequence. Cool? So I think we're pretty on top of that because we did arithmetic sequences last lesson. That's pretty self-explanatory. The real teaching moment is in this, the geometric sequence. And the difference between the arithmetic sequence and the geometric sequence is rather than adding a common difference, we're multiplying by a common ratio. So a geometric sequence is all about multiplying by a common ratio, whereas an arithmetic sequence is all about adding. Now thankfully many of the values mean the same things in the formulas, and we're given these formulas. Now because they're on our formula sheet, I'm not expecting that we won't learn these. What I'm expecting is that we understand the difference, we can identify what is an arithmetic and what is a geometric sequence, and then shove in the values and rearrange. Cool? In any one of these problems, you'll be given all the variables except for 1, and you'll have to find it. Cool? So it's the multiplication of a common ratio. This is an example. 1, 2, 4, 8, 16, 32. We can see the pattern there. So that is our geometric sequence. What is our common ratio here? 2. Because every term is being multiplied by 2 to reach the next term. Does that make sense? The equation, T1 is still our first term, N is still our term number, but in this case we've got R, which is our common ratio. So I really didn't need to write T1 and N, did I? It gets a little bit trickier when we start looking at the sum of a geometric term or the geometric series. So all that is doing is exactly the same thing that we were doing before with our arithmetic series, but now we're looking at our geometric sequence instead of our arithmetic sequence. So for our geometric series, and again this is given on our formula sheet, T1 multiplied by R to the power of n minus 1 divided by R minus 1. No new terms there, correct? The only thing that's different is that we've got our n in our power. So the sum of all previous terms in a geometric sequence is our summation there. When r is greater than 1, what happens to our, as we go off to infinity, what happens to our series here? Look at this series, right? Is r greater than 1? What's going to happen as I go to infinity? It's going to get larger and larger and larger, so the value is going to get further and further away. So it's going to become infinitely big, correct? So the sum diverges, and you might put it in brackets. Oh, I'll just leave diverges. I don't know, it's complicated. Because the first term is negative, it also gets increasingly large. But the values get further and further away depending on which way our first value starts. What about if r is less than 1 but greater than 0? So let's say r is 0.5. Let's look at this example. I'm standing on this far side of the room. I usually do this with a kid. I'm allowed to leave this room when I exit the door, but I'm only allowed to walk half the distance between me and the door. Do I ever get to the door? Why not? Yeah, so every time if I'm multiplying by a decimal value, a value less than 1 but greater than 0, I will eventually reach a point where I don't really go any further, correct? So rather than diverging, the sum converges. And this is pretty important to understand because that's where we've got this equation here. And I'll explain that in a second. But it converges. It gets to a point where it doesn't really change. It doesn't go up or doesn't go down. Cool? Because by the time I get to right here, half the distance to the door is barely anything. It's negligible, correct? So that's what happens in those geometric series. What about when r is a negative number? Have a think about, I'm going to give you 10 seconds to think about what would happen if we're multiplying by a common ratio that is negative. What do you reckon, Sarah? Have a think. What happens when you multiply a negative number by a positive number? Get a negative number, correct? So then let's say term 2 is negative. Then we're going to multiply that by a negative number. A negative number by a negative number is a?
Positive.
Okay, so it's going to go negative, positive. What's the next one going to be?
Negative.
The next one?
Positive.
Next one?
Negative.
What's it going to do? Like zigzag. We call it oscillating, but zigzagging. I'm happy with zigzagging. Alternate, oscillate, any of those sorts of words. It goes up and down because of the nature of multiplying by a negative number. If you're a negative number, it's going to make a positive. If it's a positive number, it's going to make a negative. Cool? Every consecutive term is going to swap in signs. So that's our geometric sequence, a geometric series. Like I said, we need to remember these formulas off by heart.
No.
What do we need to know?
How
How to use them. And the hard part is in an exam is it's always going to tell you it's an arithmetic or a geometric sequence. It's about identifying what type of sequence we have. Once we know what type of sequence we have, it's just about shoving in the values. Cool? In this case here, why can we get a value? Pretty sure. Why can't we get a value in this case? If it diverges, will it ever reach a stopping point? This one, will it ever reach a stopping point? It's going to be up and down, up and down. But this one here, there will be a point, like I said, where there's going to be a finite point where I stop at that door, correct? So as a result, we can determine the geometric series to infinity, providing our ratio is less than 1 but greater than 0. And it's the same thing there. Cool? In the past, I've sort of broken down how we determine that formula, but I wouldn't worry about that because all we need to do is identify the ratios between 0 and 1. In the formula sheet it has this. That's exactly the same thing. Cool? Actually, not quite the same thing, but anyway, that's okay. It's really negative 1 to 1. Either will do. If you have a situation that looks like that, then you can apply that formula. So it's about saying, am I asking for the sum to infinity? If the answer is yes, it's probably one of these. You just have to check that your ratio is between negative 1 and 1. Sweet?
Is that the same as that?
No, slightly different equation.
Is that between negative 1, so instead of just positive 1?
Yes. Yes it is. Thank you. Cool? But again, all on your formula sheets, so make sure we are aware of that. What's the real trick? What's the real trick? The hardest part of any of these problems when you're sitting in front of an exam is knowing that it's a geometric or an arithmetic. So how do we know if it's a geometric? You've got a multiplication, so there's a repeated multiplication going on. How do you know if it's an arithmetic? You've got a repeated addition. Now this doesn't always mean that it's getting bigger, correct? Can a geometric sequence get smaller? Yep, it can also do this. Cool? Does that make sense? And in situations where R is between negative 1 and 1, eventually it'll hit a point where it stops. Converges on point. Sweet? Are we happy with that? Let's go. Works on Google Classroom, I'll put it up.